How are you? I'm
good. I was starting 25.
Are you reading?
No, I am drinking with last week.
Oh, yeah.
I'm just too long.
Good evening. We're very pleased to welcome this evening Professor Buchmueller from Imperial College London and also visiting professor at Oxford. His research focuses on dark matter, gravitational waves, and fundamental particles. Without further ado, I'll hand over to Professor Buchmueller.
Yeah. Thank you. Well, first of all, thank you very much for the introduction. Great pleasure to be here today and to discuss with you what I believe are great opportunities to explore the universe with quantum technology. Before I come to this in a bit more detail, this is my personal shopping list of what I think are really important open questions in fundamental physics. But it's also fair to say that everybody can come up with his or her own shopping list of open questions. But one thing to realize is that in the last 2 to 3 decades, mankind really has made an effort to set up a comprehensive set of technology and tools in order to go after these open questions of fundamental physics. One example are big colliders. I mean, this is my background. I am still working a significant fraction of my time at CERN at the Large Hadron Collider. This is when we are colliding protons to bring them up to the highest possible energies to study conditions that must have existed at the beginning of the universe. What I would like to do today is to show you that there are other technologies, emerging technologies, which could potentially complement, not replace, but complement the program we have already established in order to study these fundamental questions. And that brings me straight to quantum technology. As I'm sure all of you know, quantum technology or quantum physics really goes back to the beginning of the 20th centuries, where in particular these two gentlemen, aided by several others like Albert Einstein, but also Pauli and others, started to develop a quite fascinating and relatively unique at the time and still not easy to understand theoretical framework, namely quantum mechanics. Then it took several decades for that theoretical framework to really then start translating into real-world technology applications. Clearly, the first one was the transistor, hard disk, and lasers, things we are utilizing today, and they do come out of the understanding of the quantum world and the properties of the quantum world. Now, many people believe today that we actually have entered the second quantum revolution, and that is now really been driven by the fact that in the last 10 to 15 years, we have made enormous progress in understanding and developing quantum sensors. And quantum sensors are, devices that work on the quantum level, but will eventually reach enormous precision going well beyond the conventional technology. One example are atomic clocks. This is the real example we have today where a quantum technology has really reached what we call quantum advantage. That means it goes beyond the classical technology. It's the only example we have today. Atom interferometry is the other quantum sensor I would like to show you, is reaching this point, and obviously longer down the road then there will be hopefully quantum computing being unlocked with reasonable error correction and then also taking quantum advantage here. But today I'm really going to focus on quantum sensors, in particular on 2, atomic clocks and atom interferometry. Now, out of that list, I could have picked several items out of this list to illustrate to you why this quantum technology could be quite helpful, but I've picked one which I think is the most prominent one out of those questions which I've written down, and that is what gravitational waves tell us about the universe and its fundamental laws. As I will show you in the course of this presentation, the discovery of gravitational waves in 2016 really opened up a new tool of understanding and possibilities for us to really learn about the beginning of the universe. Gravitational waves are not only a signal, but really a tool now to learn many interesting things. So this is a particular interesting subject. Now, when it comes to gravitational waves, obviously we have to go back to general relativity. So when I told you that we have seen in the last century a year of quantum mechanics or quantum physics development, it was also, and quite independently so, a century of general relativity. And according to Einstein's theory, as I'm sure you're all familiar with, gravity is not really a force, even so we're still treating it as a force, but we haven't found the exchange particle yet. But it's related to the curvature of space-time. That's the basic concept of general relativity. And to put it in the words of John Wheeler, matter tells space how to curve, and space tells matter how to move. So that means if you take this serious and you have very massive objects that are moving through space and time, should I come closer here? That are moving through space and time, like for example, supermassive black holes or just black holes with a couple of hundred solar masses, space will have to bend in order to accommodate the movements. And if you really then think this through, and you have, for example, a binary system of two black holes which started to capture itself in the gravitational environment, then when they start rotating, they will basically bend space-time, and it will create what you could refer to as ripples in the space-time continuum, or more physically correct, we call them gravitational waves. And if you really look at the general equations of the equations of general relativity, right after they were published, I think it took just a year, it was immediately realized that such a concept of gravitational wave must exist for general relativity to be correct. So these ripples of space-time or gravitational waves are important. Now, how are they being generated? That's a little video which is from LIGO Virgo, which shows you a little dance of what you could think of two black holes, one supermassive one and one not so massive one. And you basically see, because of the space-time bending, you generate this wave, which is starting to penetrate into the universe in space-time. And because of that, there is an energy loss in the system of the two rotating. Because of the gravitational wave, it releases energy. So they come closer and closer to each other. They start spiral up faster and faster. And therefore, you have the characteristic behavior of a wave that starts really then collapsing at the end towards the final merger. And then you will see in a second, then what you will get is the final ripple in the space-time. This is what LIGO and Virgo have been utilizing to measure actually gravitational waves at the end of the merger. So that is a fundamental principle. And this general relativity is true. These gravitational waves must exist. Now, what would the gravitational wave do to Earth? If a gravitational wave then arrives at Earth, it would start really penetrating and changing the space-time environment of Earth. Now, this is a very exaggerated example of how this is going to happen, and this was the final merger at the end, but effectively this is what happens on a much smaller scale. So really the entire space-time continuum of Earth is being changed when these gravitational waves go through. Now, the effect is not so big, so we had to develop instruments, and the most prominent instrument is laser interferometry, as you can see here. So you have a laser beam, you start shining the laser beam to various different to two different arms, as you can see here. So the laser beam here is, there's a mirror which splits the pathway, and it's been reflected here. So the laser light comes back, and again it comes to the mirror, and then the mirror is focusing it to the detection region. And in the detection region, then you're measuring basically the wave fringes. Now what happens, you can focus on here, if a gravitational wave passes through, it will change very slightly the length of the arms, because of the penetration of the space-time continuum. And that is then what you can see here in interference patterns. So you measure the interference patterns, and from the interference patterns, you can deduce whether or not a gravitational wave has essentially passed through. Now, how big is the effect? To illustrate this, it's relatively easy to calculate it. I don't want to go too much into the details. But effectively, if you use the example of the first detection of a black hole merger or of a gravitational wave mankind ever has done, then it's basically, these are the basic parameters. Both of those black holes had around 30 solar masses, so they were 30 times heavier than our sun when they started merging. Now, if you calculate how big of a length change you would have to measure, which is called the strain of the gravitational waves, a relative length change normalized to the total length of your measurement device, then you can calculate that the strain sensitivity you have to reach is around 10 to the minus 21. So now, if your instrument would be a meter, that means you would have to measure a change of 10 to the minus 21 meters. That's an incredibly small number. Now, it happens to be that these gravitational wave detectors were not just meter long, but they were really built over kilometer scale. So you're reducing the 10 to minus 21 to a requirement of 10 to the minus 19 meters, but that still is an enormously precise instrument you will have to build. Now, what is actually 10 to the minus 19 meters? It's quite surprising, and I'm always been shocked when I look at this. So take this little white bar here as a reference system of a meter. Now I start dividing this by a factor of 10,000. Then I'm reaching basically the dimensions we have for the thickness of human hairs. So we are looking here at hundreds of microns. I again divide by a factor of 100. Then I come to the domain of wave light, laser light. That's the wavelength, which is about a micrometer. Then I divide again by a factor of 10,000, and I come to the atomic diameter, which is around 10 to the minus 10 meters. I divide this again by a factor of 100,000, so I come to the diameter of a proton or a neutron, I mean those objects which are forming the nucleus of an atom. That's already incredibly small at 10 to the minus 15 meters. And then you divide again by a factor of 10,000 to reach the 10 to the minus 19. And that's the level of measurement LIGO worker had to do in order to measure a gravitational wave. It's incredibly precise. It's probably one of the most precise instruments besides atomic clocks who have ever been built as humans. So we should actually be proud of it. And quite rightly so. These three gentlemen here, not so much for the theoretical development, but really for building the experiment, got the Nobel Prize because they were the ones driving the understanding over 4 decades. It took 40 years to really develop the technology to the level that this 10 to the minus 19 could be measured. So this is an entire career of an individual, even a bit more, but it was worth it because mankind has learned a lot. And today we have a quite diverse landscape of laser interferometers. So there's the 2 big LIGO versions in the US. It's complemented by Virgo in Italy, and lately Kakra, our Japanese colleague, have joined the network. So we really have a distribution of laser interferometers across the globe. I'm also showing you here Geo60, which is not part of the network, but it has been the first prototype version being built in Germany to really start demonstrating that this technology actually can be done. So it played an important role. And because of the discovery, and because of the ability of this technology, I think we have now very good reason to believe that we can measure now gravitational waves from various different frequencies ranging from 10 to the minus 19 hertz to 10 to the 11 hertz. So this is an entire new observatory we can use to start learning about the universe with various different techniques. Now, the one I would like to really focus on is basically this regime here, 10 to the minus 4 to 10 to the 4 hertz, which is where we believe a lot of fundamental physics might be hidden in the imprint of this gravitational waves when they were generated at the beginning of the universe. Because they're still there, they carry the information of how the universe was generated. We just need to be able to measure them and to learn from it. Now, if we look now at a magnification of that range, so this is now 10 to the 6 to 10 to the 4 hertz, frequency hertz. I'm summarizing here now where we are experimentally in terms of measuring gravitational waves. So this is the characteristic strain of a gravitational wave. So that was the 10 to the minus 21. If you remember, I was introducing to you, this is how much of a change you do normalized to 1 meter in terms of a length reference. This is where we today can measure gravitational waves. So we have sensitivities of black hole mergers of around 60 to 100 solar masses. So that's, you add the 2 black holes together, so then you get 60 and 100, so 30 plus 30 was the example I showed you before. And this is how these signals will evolve in that diagram. So this is when they start rotating. They captured it either for the first time, they start rotating. So that's when the signal will start to evolve. And at the end, you will get this little chirp, which is then the ripple, the big ripple that goes to space-time, which LIGO and Virgo have been using. Now, we are fortunate enough to have a planned program that people are currently looking at, again, based on laser interferometry. So terrestrial program is to improve LIGO and Virgo sensitivity with the help of instruments which will be in the underground and even bigger, the so-called Einstein telescope. That's how we refer to it on the European side. The US calls it Cosmic Explorer, but the idea is the same. Again, 2 experiments, one in Europe, one in the US, operating in tandem. We are even more fortunate that the European Space Agency eventually, after 30 years, committed to the LISA program, which is a satellite-based laser interferometry, which is currently under construction. So this is not anymore hypothetical. It will fly in 2035. Which will cover a very interesting frequency range for, in particular, very high astrophysical objects, solar masses of 10 to the 7 times the mass of our sun. So this is really big objects which are generating ripples. But when I looked at this plot in 2016, shortly after the discovery of gravitational waves, this is when a lot of my thinking at least had changed, because we went from hypothetical, we don't know yet, to we can measure gravitational waves, so what can we learn from it? I looked at that plot and I realized one thing, as we would call it in London, namely mind the gap. There is a significant frequency gap, and actually a frequency gap in a very important frequency region, which is very difficult to cover with laser interferometry. Despite all the technology improvements we have done, it's hard to build these experiments for a very simple reason, in particular around the 1 to 10 to the minus 1, 10 to the minus 2 hertz region. Now, it happens to be that if you look at the technology options, there's not many technology options out there that can actually do that, with the exception of one, and that is atom interferometry. So when I looked in atom interferometry and started to do some projections of what a kilometer experiment, a shaft experiment in that time, so not the horizontal one, but the shaft, because we need free fall time of the atoms, could reach, you can see I can dial basically the frequency range such that my atom interferometer experiment will cover this mid-frequency region completely. So it will be a complementary technology. And I will show you later, if we have enough time, why this mid-frequency range is so particularly important for our physics understanding. Now, the next step would be then, and this is also something we have been doing in development together with NASA and ESA. I was writing down a space mission profile, a white paper of a space mission profile of how such a space mission could look like. And if you would bring it to space, you could even increase the sensitivity, and that's what we have baptized EDGE even further. So that is where atom interferometry conceptually now comes in as a quantum sensor that can help us to fill a gap in a very important frequency range, which prevents us otherwise to really learn more about the gravitational waves in this region. Now, how does atom interferometry actually works? Now, it's also something I had to learn. You know, my background is particle physics. So I spent basically the last 10 years to learn cold atom and atom interferometer physics, which is interesting, but also challenging. Now, to start out with, in a very simple way, I think the easiest way to introduce atom interferometry is to compare it with light interferometry, because that's something we understand. You're being taught that at university. I hope Cambridge is doing that as well, but I'm pretty sure they are. Where the active element is laser light. You shine this on your beam splitter. You take the laser light in the 2 different paths. You use mirrors in order to reconnect the laser light, and then you observe the light fringes because of the wave character of the laser light. So from the light fringes, you can then deduce whether or not something differently has happened between arm 1 and arm 2. Atom interferometry is conceptually the same. However, now the active element is not laser light, but atoms. And it's not just one atom. It's actually a huge amount. It's a cloud of atoms. Today, we are reaching around 10 to the 6 atoms, typically in such clouds. We are aiming for 10 to the 10 atoms eventually. But these atoms are not just atoms. They're ultra-cold atoms. They're really cooled down to the coolest possible temperatures we can achieve. And that's one of the interesting advantages about cold atom physics. You don't need a fridge. You do laser cooling. You use lasers in order to cool the atoms in their movements. So you reach temperatures which we otherwise with fridges would never reach, which is quite incredible. So you start out with this ultra-cold ensemble of atoms, and now you have to construct a beam splitter. or a splitter, the equivalent of that. And it happens to be that, again, lasers will be quite coming handy with a so-called pi-half pulse. You will be able to split your ensemble of atoms, half of them in the excited state and the other half remain in the ground state. And this is how you then start opening up your trajectory. The mirrors are again constructed with so-called pi pulses. So then you're flipping the excited state to the ground state, and the ground state goes to the excited state. And at the end of the day, you have a final pi-half pulse to focus the two beams again. And what you're measuring now is not light fringes, but due to the wave character of quantum mechanics and of the atoms, it's atom fringes or matter fringes. And again, you can exactly with the interference patterns in the same way basically learn if something differently has happened between the two different instruments, between the two different arms. So this is how it would look like in a shaft experiment. And there are several of those towers already available. The biggest ones we built today are at the level of 10 meters. For example, at Stanford University, the most prominent one is from the Kasavich group. It's a rubidium 10 meter, in which you launch the atoms, you give them a kick, they follow in this parabolic environment, then you start basically here, your atom interferometer sequence. So this is the ground state, this is the excited state, and this is just being replicated here. The bottom line is, as longer you can interrogate the atoms, as more sensitive you will be. As bigger you can separate the two wave packages from each other, which are not in an entangled state, but in a superposition. They remain in the superposition until I collapse the wave function at the end. And the high flux, basically meaning the number of atoms. So these are the three things you would like to maximize in order to increase the sensitivity. Today, these instruments are the most precise instruments we can build to measure little g, because they're extremely sensitive to the variation of the gravitational field of Earth. So they are as sensitive as atomic clocks, but atomic clocks will still have to use general relativity in the ansatz of change of height, basically. So that's one of the interesting things and how to set it up. So this is not science fiction. We built these instruments and we have them on the level of 10 meters, but bringing them to the right precision is important. Now, one atom interferometer or one atomic clock, the two are very much related, will not do the job. It's the same like with LIGO and Virgo, where you need two arms in order to cancel out some of your noise structure. You will have to do the same with atom interferometry. And in that Gedanken experiment, I make it simpler. I go back to atomic clocks because they're simpler to explain. But you have to believe me that the same analogy can be applied to atom interferometry. So I have two atomic clocks in this Gedanken experiment, which are really far separated from each other. So you can think of one is your reference clock and the other one is your measurement clock. Now, these atomic clocks are being made out of one atom. Let's call it strontium, because that's what we are using, which has a ground state and an excited state and is separated by a frequency omega alpha. Now, I start my experiment. I apply this so-called pi-half pulse across my two clocks. So there's one common laser beam, the pi-half pulse, which splits the ensemble in my clock, half of them in the excited state and the other half stay in the ground state. Then I start my experiment. The two clocks are traveling through space and time. At the end of my experiment, I'm again using this so-called pi-half pulse to synchronize the two clocks. Now, if you write down, who has had quantum mechanics already? All of you, okay. So if you write down the Schrödinger equation for an object that travels freely through space and time, you can see that this object on the excited phase on the excited state will accumulate a phase, an imaginary phase. That's a pretty simple thing. And that's essentially what happens here. So you will get an imaginary phase. And in our example for that is the imaginary phase is basically made out of the time we traveled through space and time and omega alpha, which is the separation in frequency between the ground and the excited state. Now, if I compare my two clocks and measure the time, or better, the phase, I will get a null result if nothing has happened. Now, what happens if my measurement clock is now exposed to the environment of a gravitational wave? So if the environment of a gravitational wave is penetrating the clock's space-time continuum, then there will be a change of length. that change of length, because the speed of light is constant, will, for the clock, automatically translate into a change of time, a delta t. And that delta t will be proportional to the strain sensitivity of the gravitational wave and also its frequency. And that means if I now compare my two clocks, this one will have a delta t being imprinted. So by comparing the two clocks, I measure back the delta t. And out of the delta t, I can measure the frequency of the gravitational wave and the strain of the gravitational wave. So that's the general concept. Now it happens to be, and that is interesting, that with the same experimental setup, another potential interesting question about the dark universe could be answered, in particular related to dark matter. Now, dark matter can come in various different theoretical incarnations, and I don't want to go too much into that. I mean, the past 20 years I have spent on looking for supersymmetry and dark matter candidates on colliders. Promise you I didn't find anything. So this is a different frequency range in which dark matter is not really anymore a particle, but it is so light that you can really see it as a wave, a classical wave. So this is called ultralight dark matter. And that classical wave, if that is being realized, will essentially surround our Milky Way as a dark matter halo. So it is here all the time. We just don't see it because the interaction it has with us is extremely weak. But it will interact with the atoms if it does exist, and it will imprint its characteristic frequency, which is basically the underlying mass hypothesis of the dark matter candidate, on the properties of my atoms. And it will start changing the properties of the atoms according to its underlying frequency, delta omega alpha dark matter. So you will get basically an oscillation in the atoms, which is really minute, but that's the way how you could measure it. And then, again, in this experiment, if that would exist, it will imprint at the phase, but this time not on the time component, but on the frequency component. If I measure it back, I can say something about dark matter, if it does exist in that frequency range. Now, this is all hypothetical, and we had to make that real. We had to demonstrate that you can actually build such instruments, and this is a long way. You remember I showed you the Nobel Prize. It goes back to 40 years of development, so we shouldn't believe that we can do this overnight. So it will take us quite some time, and hopefully not 40 years, because that would be beyond my retirement age. But it will definitely take quite a while to come to that level of sensitivity. But we're making very good progress. And the UK made a significant investment in the development of this technology for that particular purpose. So I'm leading this AION consortium, which also is very prominent here in Cambridge. Ulrich Schneider and Val Gibson have been the ones leading the AION part from Cambridge University. Val has now been retired, so it's Ulrich Schneider basically. So it really brings together the big players in the UK university landscape. So you have the Quantum Hub in Birmingham, Liverpool University, Cambridge University, Oxford University, Imperial College London, and King's College London. And last but not least, one of our big national particle physics laboratory, the Rutherford Appleton Laboratory, which joins forces to develop the first prototype technology. So that is something we started, or I started in 2018. Before we then got funding, we were, because of the COVID period, and in 2021. But right from the beginning, and that's also interesting, we were starting to team up with the US, because in particular, led by Stanford University, there was the similar development and ideas being developed in the US. And right from the beginning, we were building a partnership between the UK and the US, so to really then include also Stanford University, Johns Hopkins, Northwestern University, Chicago University, and the two big national particle physics laboratories in this whole thing. We have signed that agreement then in 2023. I don't know how much you're familiar with that. This is the director of Fermilab to the left, but that person you might know. This is Mark Thompson. He was the former director of our funding agency, STFC. He happens to be a Cambridge professor in particle physics, quite famous. And he will also be our new director, incoming director of CERN. So you can see there's a lot of particle physics activity really behind the idea of building these large-scale atom interferometer instruments. AION is really a big dream. I thought, well, when you develop it, why not dream big? So it has 4 stages. The first stage, we're almost done with the first stage, and I wasn't even sure in 2018 we will come to that. That is building a 10-meter detection system, or just the blueprint for it, and to develop the existing technology and to prepare for a 100-meter experiment. Stage 2 is then really a 100-meter experiment where we're actively looking at potential sites in the UK. The Bowlby Mine would be one, but also at CERN. And ultimately, what you would like to do is to bring that technology on terrestrial level to the kilometer scale. But as I said, because of the t-squared I showed you before, because how long you can interrogate the atoms really goes and drives the sensitivity. If you were in free fall, where I have unlimited time of interrogating my atoms, that would be the best setup. So going to space is really the ultimate sensitivity. And as I said, we have been working together with various different funding agencies, but also ESA and NASA to start developing this. Now, this is how the AION collaboration basically looks today. There's more than 60 people. So that was a picture in fall 2021 in Oxford when we had our collaboration meeting, first one after COVID. Why I'm showing you this is because it's relatively unique, that collaboration. It's the first time in the UK, and to my understanding, probably worldwide, where we really bring 2 very different physics communities together. On one hand, fundamental physicists like myself. On the other hand, obviously those people who know how to build atomic clocks and atom interferometry, cold atom people like Ulrich Schneider, for example. So this is a new formed community where, in particular for PhD students and young career researchers, early career researchers, they have the opportunity now to learn from 2 very well-established communities which otherwise have never been talking to each other. But now you can learn fundamental physics and quantum technology development at the same time, which is an interesting subject. So the goal is really to build a 10-meter instrument in the Beecroft building in Oxford. I don't want to go too much into this. It's probably not too interesting for you. But we have a full design now. This is how it would look like. So this would be the 10-meter and how to face it. And here basically is direct access to a laser laboratory to drive the instrument. And we are now basically looking at the first more than 30 months now. I don't know when I did that slide. It's like we're 36 months past the initial phase of the project. And one of the big things we had to do, and I don't want to go too much into the details, is to build 5 of those laboratories in the UK. 5 laboratories which will be able to do the R&D we need to push the technology. So we had to build one in Cambridge, Ulrich Schneider. That was happening in July 2022. Then one at the Quantum Hub in Birmingham, one at Oxford University to drive the 10-meter instrument, and the other one at RAL, Rutherford Appleton Laboratory, and last but not least in my lab at Imperial College. So these 5 labs were built with unprecedented speed, 24 months to bring them to commissioning. And we are starting today. I don't want to go too much into the details because none of us is a cold atom physicist. Or are there some cold atom physicists? No, probably not. So we are really producing important outputs. So these are atom fringes. This is when you measure the atom interferometer sequence. This is the first time that we have done the atom interferometry on the clock transition in free fall. The clock transition of strontium, if I would have a bit more time, I would explain it to you, because our idea is really to marry the 2 technologies, use the enormous precision power that atomic clocks have reached, and integrate this into atom interferometry so that you can really measure the gravitational waves over a large region of parameter space. So marrying the 2 technologies was a very important aspect, and that's the first demonstration of atom interferometry on the clock transition of a strontium clock. And this is now a bit complex, basically shows you the differential measurement I showed you before. So this is now the differential measurement. The red and the blue is what you get from the 2 different clocks. Now, these are 2 different atom interferometers. And when you subtract the 2 from each other, you basically need to get a null result. So that's been shown here in various different forms. And this is basically the differentiation. And if there would have been a signal which would be strong enough, so it could not have been a gravitational wave because it really would have started moving Earth quite a bit, then you would have seen something like this in the patterns it's being there. So that's an important aspect. So this is what we have been accomplishing so far. Don't want to go too much into the details, but certainly building 5 labs and each of those labs has by now 4 or 5 PhD students and at least 2 to 3 postdocs, has really, increased our capabilities of doing this technology development in the UK quite dramatically, as a matter of fact. Now, I have to admit that the UK and the US are not the only ones looking into this. I mean, there's other nations which are investing quite substantial national funding into this. So we have the French building a 100-meter horizontal atom interferometer system as a prototype. Our Chinese colleagues who have invested huge amounts, undisclosed, but huge amounts in that technology, really building already kilometer scale to 100-meter scale instruments. Nobody really knows how far they are, but it looks quite impressive, again, for fundamental physics. And also the Germans have already built a 10-meter tower with a slightly different focus than what we have in mind, but nevertheless, towards atom interferometry for fundamental physics. So bringing all of them together was one of the things I felt was very important. Again, I don't want to go too much into the details, but it's never good if you have national funding and the national funding is evolving and it happens in different countries and the people are not talking to each other. For fundamental science, you just lack the synergies that need to happen in order to build such big instruments. So we were forming an international collaboration. I make it short. This is now the international collaboration. It's not a small thing anymore, so it's really big. People are buying into the idea of building this instrument. So there are 55 institutions from 21 countries which have joined forces to build this TVLBI, terrestrial very large atom interferometer baseline experiments for gravitational wave and ultralight dark matter detection. So this thing is becoming real, and depending where you go and have an interest into that, there will be a lot of institutions which are supporting these activities. So if that is an interest, keep that in mind. We're actively looking for sites of where to host such an experiment. So this is the Bowlby Mine. Bowlby Mine is an official underground laboratory of the UK, funded by UK government money. And they happen to have 2 interesting shafts. One is shaft 3, which is a part of the mine, which goes down 150 meter, which could be hosting a 100-meter prototype. And then there's shaft 1 and 2, which are on the kilometer stage. So these shafts do exist. And we don't have to dig a 100-kilometer shaft to build the experiments. We would reuse mine shafts, which are available across the world, as a matter of fact. Also, CERN has an interesting 100-meter shaft. Don't want to go too much into it, but that's at the moment the most realistic option for the European community to build a 100-meter instrument, in my opinion. Interesting. 100-meter instruments. Now, if you have a 100-meter instrument, you could already, in that frequency range, basically start seeing new signals, which we haven't been able to see before, because this is what LIGO covers, and nobody has been looking into that signal range. Now, whether or not a 100-meter experiment is then enough to see gravitational waves, we do not know, because nobody really can predict what the strain sensitivity will be in that frequency range. We know it will be there. Other kilometer options in Switzerland and across the world, don't want to go too much into this. Another thing, maybe coming to the end then, I don't know how long, no, still have 15 minutes or what? Don't want to take too much of your time, is to bring this technology to space. So I realized that actually before I was initiating this terrestrial community building process, that bringing that technology to space is the ultimate goal, and we really need to work on that. So in 2019, it was COVID times. It was a virtual workshop. It was meant to happen at CERN, but then it was happening basically virtually. We were bringing together everyone who has an interest on exploiting that technology in space. Quite a lot of people came, but most importantly, we have developed the roadmap. Government agencies like ESA and NASA do like roadmaps. That's one of the things when you come to a certain age and you continue in academia, you will realize roadmaps will be important. So we were establishing a roadmap, which is very complex, so I don't want to go too much into details. But obviously one important point, and that's the end step in this roadmap, which is 2045, was this mission proposal, which I showed you basically already, that enables to push further down the gravitational wave sensitivity in the mid-frequency range. This is how such a proposal would look like. I was writing this, I think it was 2019, 2020, I don't know. So you would have 2 satellites, not 3 like LISA, but 2 satellites, which would be in mid-Earth orbit, which will have a line of sight, and the separation of them will be around 10 to the 7 meters. And in each of those satellites, you will host an atom interferometer and a laser beam connecting the two. So you basically have now your 2 clocks and the laser beam really literally separated in space. And that will do basically then the measurement. So that is reasonably advanced in the development, and we continue talking to ESA and NASA, but everybody knows that this will be one of the L missions, large missions, that ESA, if it will fly, will be not before 2045. And that's then the sensitivity you can get. Now, why do I focus so much on the mid-frequency range? And this is now back to physics. That's one of the things which drove me in 2017 then into really looking into this in detail. You know, that's quite a significant change. I'm well established at CERN. I'm still living at CERN. I have a house in Geneva. My family is there. So changing my focus to that had to have a reason, had to have a good physics motivation other than just developing quantum technology, which is fascinating, but that wouldn't be a driver enough for me. It's basically this. And that is, I think, one needs to understand. Once you're in this mid-frequency range around a hertz, which cannot be covered by laser interferometry, astrophysical sources like black hole mergers or anything, just by the nature, will have lifetimes of measurement signals which are not this microscopic chirp at the end that LIGO, for example, measures, which is milliseconds, but they will have lifetimes of days, weeks, and months. Now, when you have days, weeks, and months, and you can follow that signal, then you will have the rotation of Earth around the sun. So you will be able to triangulate directly where the merger happened in the universe. And that is our biggest problem. Because in order to learn really about the physics that happened, we need to be knowing where the signal is coming from and really put all of our direction devices into that direction. Neutrino detection, photon detection, gamma ray detection, gravitational wave detection, multi-messenger physics. Only when you get everything at the same time, you will be able to really learn what happened there, rather than just having one of the sources. And that has been a big, big, big problem. And LISA is not solving that problem either, because LISA, which sits very low in the frequency range, will have lifetimes for observation of 100,000 of years. Now, it doesn't really help me to say that in 100,000 of years, please point your experiments in that direction and you will see a merger happening. That doesn't help. So weeks to months is the lifetime for us humans in which that thing makes a lot of sense. And that mid-frequency range will unlock ultimate multi-messenger physics. And that's why it is so important to really cover this. If we would have had a mid-frequency range experiment already at the time when the first gravitational wave, which is GW 115914, was being measured, we would have had enormous precision weeks before the merger happened to tell it will happen over there. And we would have learned so much from it. Still today, we're not able to do that because we don't have the instrument. Obviously, making a network like between the US and the UK also is an interesting thing. And that is what I'm dreaming of. If you take all of those together, laser interferometry, cold atom interferometry and everything, that is how that plot could look like by 2045. Really comprehensive coverage with all the knowledge that we can get out of it, of whatever then might have happened at the beginning of our universe, astrophysically, but also cosmology-wise. Another little side remark, so that this technology development is not totally lost just for fundamental physics, is that when we built the roadmap, one of the things which I found very striking, and it's probably still underrated, is there's a lot of potential of measuring with this technology the gravitational field of Earth. I showed you before, when you have an atom interferometer, it basically is directly sensitive to little g. This is what it measures if you have that set up in the way we're operating it. And it can be done enormously precisely. And one of the big problems I think we're facing when it comes to climate change is, obviously, we know it's getting warmer, but nobody has really predictive power in terms of models to show How does it get warmer? What is the driver? There's a lot of diversity, and this is coming from even from the NASA one, of very different models which are out there, which all have vastly different predictions of how the climate, based on our current data, is evolving. And what is that the case? It's very simple for any scientist, because we lack data. We lack data to constrain these models. And that is the biggest problem. We're all trying now to fight climate change rather than to understand it. We need to understand climate change better. And for that, there is one way of doing it. There is already a modest space program out there which gives you observation called Earth observation data, which we're using to constrain climate change. But the real biggest impact one could do is by basically measuring the gravitational field of Earth and mapping it very precisely. Why measuring the gravitational field of Earth? Well, by measuring the gravitational field of Earth very precisely, you have access to what is called equivalent of water height. And the equivalent of water height, that's what's been shown here, can translate in many different aspects, in climate change, flooding, whatever it might happen essentially in there. And what we can resolve of the Earth, you can barely see the Earth today, is basically because of the drifting of classical instruments, not much. We can't see any detailed aspects of the Earth in terms of climate change. Now, what would happen if we bring the technology which we have in the lab today into space and do the same kind of observation? You would have a much more accurate resolving of the water heights and hence much more data to constrain your climate change model. So that's one of the things we're really working now with ESA and NASA to convince them that this is a good way forward. But frankly, these are government agencies, so they are slow and they are also quite risk averse. So new entities, even though I don't like to put his name out there, but people who have been inventing SpaceX, who are much more aggressive in the way of bringing up satellites, that would probably be the right way of essentially pursuing this. And we're talking to private investors now also to see if there's an interest on doing this. I think I'm just coming to the end because I mentioned already dark matter. I don't want to go too much into it, maybe just showing you this plot. The same program we do for gravitational wave could also be done for ultralight dark matter. So you can really carve out a complete uncovered territory where we could do discoveries. Nobody knows if that's the right kind of dark matter we're having here, but it's certainly a worthwhile goal to also do this. So there's many other things you could do with these instruments extremely precisely. One thing we're working on is probing dark energy, because also for dark energy, these atom interferometers and also atomic clocks in particular are quite interesting. Dark energy is a bit less understood in terms of the theoretical framework than dark matter is, so there's a bit more speculation in it, but we're currently working with some theorists at Imperial College to write a paper of how atomic clocks could be used in order to start constraining potential parameter space also for dark energy. So I just leave it here, I think. Well, I talked enough. Thank you.
Questions? Does anyone have any questions?
You showed the timeline of going from 10 meter to 100 meters to eventually space. Is that purely because of a limitation of like funding and like agencies, or does the technology need to be developed more so you can operate in space? Like if somebody gave you as much money as you wanted, would you go up and build it right now?
If you give me as much money I want, I go to space. But it's basically a combination of the resources you get in order to build an instrument, but also the time you need in order to bring then the corresponding cold atom technology to the level of sensitivity that makes it worthwhile to have the instrument. So these are two different time axes. So I think a stage program always makes sense. You start out with a 10 meter in a lab environment, you demonstrate that the technology can work. Then you scale it in a mine shaft to 100 meter, which has some interesting physics already to be done. But instead of costing you 250 million, it costs you maybe 30 million. And then once you have demonstrated on that 30 million price tag that the technology works to the level you would like to have, well, then you make the investment into 250 to 300 million pounds to build a kilometer scale detector. So it's economy, but also the timeline it takes to validate the technology to the level you need in order to do the different goals.
like the want to face but in this like say 10 meter or like 200-meter shaft, it's like the gravity should just be passing through, right? Like there's no perfect scenario where one atom is feeling it and the other is not.
Yes,
So
that's correct. You referred to my example with my two clocks. One was the measurement clock. The other one is the not impacted reference clock. That's basically a transformation into a parameter space you can do also for atom interferometers and clocks in general when they are being hit by the same signal but at different times. Because what will happen is you have your sequence down there. Because when you launch the atoms, it will be triggered by one common laser beam. So the laser beam starts down here. It triggers my first atom interferometer sequence there. It keeps traveling up and then triggers the other atom interferometer sequence so that it imprints the same laser. So the two sequences will be separated by whatever then the speed of light and time and length will give you. So when a gravitational wave comes in, it will first imprint here. Let's say it comes from here, imprint here. It will penetrate further and then start imprinting here. So again, you will have the same time delay. So they will be in two different sequences. So then you will have, instead of the delta t being just imprinted on one atom interferometer and nothing on the other, you will have a quarter of the delta t imprinted there and 3/4 of the delta t imprinted there. So again, if I make the difference between the two, I will get the full delta t. But it will now come from both sources and not just from one getting everything and the other one get nothing. So it's just a reformation of the coordinate system. Yes, and it will be because they're at different times in the sequence when the gravitational wave passes through. But it adds up to the same delta t. The big difference is the interrogation time, because you need free fall of atoms. So if I have horizontal, my two beam lines will basically go like this. So there will be two atom interferometers. One will run here, and the other one will run here. And the maximum atom free fall time will be 50 centimeters. Now you calculate how far you can go with 50 centimeters and take the inverse to get the frequency of the gravitational wave you're being sensitive to, because that is effectively what you can do with atom interferometers. The free fall time you have to your disposal, let's call it t, 1 over t is the frequency of the gravitational wave you will be sensitive to, maximally sensitive to. So they will have 50 centimeters of free fall, which gives you 7-8 hertz if you translate it. So you're very close to the spectrum of LIGO, which just stops at 10. If you really want to have a hertz and lower, you need to have free fall times of 5, 6, 7, 8 seconds. Yeah, 10 seconds for a frequency of 10 to the minus 1. And that you can only get in shafts, or you bring them up to space. If I bring them up to space, I will build them again horizontally. It's the free fall time. There are already cold atom experiments on the ISS, mainly clocks. I think they are planning now to bring a small-scale atom interferometer up there, but the development is extremely slow because they're very much risk. I mean, ESA and NASA are basically built on zero failure. So the technology has to be developed to a ridiculous level of robustness so that nothing can happen to it. Now, with that type of technology, that takes decades. I'm not saying you should go and completely avert the idea of the technology when you bring it up, but you have to take a bit more risks. I mean, as for example, SpaceX does. It's a completely different philosophy in which they are operating. Failure is acceptable for them. Failure is not acceptable for ESA, nor is it for NASA. And that's the big problem we are fighting today. I hope private industry will make a big difference here, because if you're less risk averse, I mean, the progress we're seeing, look at what Starlink has done. I mean, if the ESA or NASA would have to do that, we would still be debating about when we are bringing it up in space, rather than having it up in space. So it's a political environment. Space agencies that are government funded are not necessarily the best vehicle to bring these things on an accelerated timeline.
Any more questions?
But don't quote me on that. I mean, I still have some.
Right? The essence of moving in one direction in particular, right? So
It will be launched. It will actually have that kind of trajectory.
so you have a lot more resolution in one direction. Does that make any difference for like the directionality of the detector? Like for LIGO, you need two, kind of just because, I mean, number one, you have to run an interference experiment. Number two, you're looking for a change in each of the arms, each of which is in a different
Correct.
direction.
So I showed that, but I didn't go too much into the detail. Because of the properties of gravitational waves, they are directional. So if you have an instrument and the gravitational wave, for example, our sensitivity goes along that line. If the gravitational waves comes orthogonal to it, you basically have no sensitivity. So what you have to do is, like LIGO and Virgo, you build a network. So I showed you before, a detector in Europe and a detector in the US, for example, will almost have a 90-degree angle. If you operate them in synchronous, you exactly have that. You have coverage in the entire coordinate system of 90 degrees. And that would be the idea. Yeah, you would not just build one of those. You would definitely build at least two in the right directions around the Earth. But you need shaft experiments to get the free fall time. But you can do that by just placing them in different locations on Earth. Yeah, Europe and the US is perfect 90 degrees. Well, that if you believe it's round.
But yesterday there was a big data release from DESI, and it like seemed increasingly likely that dark energy is evolving over time. But I just wondered what your thoughts on that are and how it relates to possibly detecting it with unexplored.
Well, I'm a particle physicist. So there's two different ways of how to approach that problem. Clearly, my rucksack gives me one way, and that is finding the exchange particle. If you believe that gravity is a real force, then there has to be a graviton. And that graviton has to have certain properties, very likely spin 2 properties. So you will have to, in order to fully understand what's happened, in my opinion, formulate a consistent quantum field theory for gravity. And that's what we in physics are struggling now since 20 years to do. We have not been able to marry quantum mechanics with general relativity. That's the problem. We have married quantum mechanics with special relativity. That's our quantum field theory, which describes very well, electroweak interactions, it describes nucleus interactions. All the other forces are very well described by that, just not gravity, because of the property that it has to have an exchange particle, which is a spin 2 particle. Now, if we do not understand that, I find it hard to believe that any other observation we're doing out there in the cosmos is something which we can have a concrete and unambiguous interpretation of what's happening. Because we lack the theoretical framework. The dark energy is for a reason being called dark, because we don't know what it is. So we have to start really building up a bottom-up approach to develop the theoretical framework, which will enable us to compare it with the data and then say, well, yeah, that's it. That's how I can constrain it. And then we may understand it. Now, you talk to an astronomer, he will probably have the completely different approach. He will say, well, no, I would only take my data and we'll learn from that data, and then we build down and build the model. It's two different ways of doing it. None of them has been leading to any conclusive answer yet, so there's still a long way to go. But I still believe that at some point, someone bright, young as you guys are, will come up and formulate a quantum field theory for gravity. And I think then we will know much more.
Thank you. Let's give another round of applause.
in the chat.